The date is June 9th, 2026. It is currently 2:34 a.m. and I thought I could do a video on electrical current. So this is a video on electric current. What is electric current? Electric current is the total charge that passes through some cross-sectional area A per unit time. So let the cross-sectional area represent a wire, a conductor. If delta Q is the amount of charge passing through an area in a time interval delta T, then the average current will be as follows. Delta Q over delta T, such that delta Q is the amount of charge passing through an area and delta T is the time interval. And remember, I stands for current. So this is what it would look like. So if we were to zoom in theory, this is all in theory, you guys, but in theory, if you were to zoom in and look inside of a wire, and these little dots here with the arrows, these vectors, well, these are going to be individual charge. And it's just showing which direction they're flowing in. This is the region A, this is the change in Q, and this is just showing that delta Q crosses A in delta T, change in time. So amount of charge passing through an area is delta Q, and then delta T is the time interval. All right, so what's the breakdown? What's the breakdown, guys? Well, if the current changes with time, we define the instantaneous current I by taking the limit as delta t, the time interval approaches zero. So the current is the instantaneous rate at which charge passes through an area. So this is what the equation would look like. We have I, the current, equals the limit as delta t approaches zero for delta q over delta t, and that can also be written as dq over dt. That is the change of q with respect to t. So the change of q with respect to the change of t. So let's just slow down for a second and try to conceptualize the flow. So imagine you're standing at a toll booth on a highway, and the cross-sectional area of the wire is that toll booth on the highway. So let's talk about the average current. Suppose that you count the number of cars, which in this case is the charges, passing through the toll booth over a full hour, which is our delta t, the change in time. If 600 cars pass in 600 minutes, then your average is 10 cars per minute. But this does not tell you if the traffic was steady or if it all just came in 1 second, if they all came in one group. Um, and so this gives you a smooth out rate. In other words, you can't pinpoint how many cars were coming through at any one point in time. The instantaneous current. So imagine that you want to know how heavy the traffic was at exactly 2 p.m. You cannot measure that over an hour. You have to look at an incredibly small sliver of time, maybe even in like something as small as a millisecond. So you are to look at how many cars pass through in that tiny moment. And as you make that time slice smaller and smaller, it's approaching zero, and you'll get the flow at that exact moment. So please look at this diagram. The diagram shows a slice of a wire and an area A. The brackets labeled as delta Q represent the total amount of charge, which is a bunch of electrons, that successfully make it through that sliver there's a typo here, forgive me. Pretend there's an R there. The sliver of an area during a time window delta t. The issue is if the flow is steady, dividing by the big bunch of charge by the time interval, the window of time, well, that works just fine. That is I sub average equals delta Q over delta T, like we talked about. But what if the flow is shaky? What if it rushes and then stops and then rushes again and stops and rushes again? You know, a big a big time window will just give you a blurry average. So why the limit? Well, the limit is the mathematical trick that we need to zoom in and look at what's going on. Imagine you keep shrinking that time window delta T. Instead of looking at a 1 second window, you look at a 0.001 second window. Then you look at a 0.000001 second window. As you make the window delta t smaller and smaller, it approaches zero. By the limit, delta t is essentially zero. You are no longer looking at an average over a duration. You are looking at an instantaneous flow right at that exact moment. When mathematicians see that limit operation applied to a fraction, they give it a special name, and that name is the derivative. Delta Q is a big change in charge. dq is an infinitesimally small change in charge. Delta t is a big change in time. dt is an infinitesimally small change in time. So when you see a textbook say dq over dt, what it means is the rate of change q with respect to time t. Now, when I was looking at this, especially this, when I was looking at this dq over dt part, I'm like, this looks like a differential equation. And so this is how you could interpret this as a differential equation. So this is how you could read it as a differential equation. If someone gives you a formula for how much charge has passed by a certain time, for example, q of t equals 5 times t raised to the power of 2, you don't have to guess at what the current is. You can just take the derivative. That is, I, the current, equals dq over dt, which is the change in q with respect to t, equals the derivative with respect to t of 5 times t raised to the power of 2. And if you take the derivative, we could, I could walk you guys through how to do this in your head. If you wanted to take the derivative of 5 times t raised to the power of 2, well, that's going to be, you're going to factor out that 5, right? And then you're going to deal with that t raised to the power of 2. And you're going to bring that t, they're going to bring the 2 out front of the t, and then you're going to subtract 1 in the exponential place. So what you're going to have is the derivative of t raised to the power of 2 is going to be 2 times t, and then you're going to multiply back that 5, and it's going to be 5 times 2 times t, and that's going to be 10 times t. So this equation tells you the current at any moment t. So if you want to know um, the current at t equals 2 seconds, you could just plug it in. And then you can have, okay, well, since it's 10 times t, well, then I'm just going to plug in 2 where the t is, and I'm going to have 10 times 2, and that's going to be 20 amperes. The unit of current is coulombs per second, but this can also be called the ampere, denoted with an A, named after Andre Marie Ampere. 1 ampere equals 1 coulomb per second. The term ampere can also be called an amp. Since the ampere is a rather large unit, current is also expressed in milliamps, microamps, and nanoamps. And then I have the scientific notation if you want to take a look at that too. Within conductors, and I put the emoji of the Statue of Liberty there because the Statue of Liberty is made of copper, and it was a gift from France, so thank you, France. Um, but copper is one of the most common electrical conductors, and so that's why I put it there. Within conductors such as copper, electrical current is made up of free electrons moving through the lattice of copper ions. An ion is any atom or molecule that has a net electrical charge. So there's cations, which are positive, and then there's anions, which are negative. Now, copper is 1 free electron per copper atom. The charge on a single electron is given by the following equation. Q sub electron equals negative E, which is another way to write it, equals negative 1.602 times 10 raised to the negative 19th power C. So this is the charge. This is the equation for the charge that's given for a single electron, right? We call it 2.2a. This is equal to, but opposite in sign of the charge of a single copper ion. The positive charge is a result of the atom donating 1 electron to the sea of free electrons that are randomly moving about in the lattice. The loss of the electrons means that there is 1 more proton per atom than electrons. The charge of a proton is as follows. Q sub proton equals plus E, which is another way to write it, equals positive 1.602 times 10 raised to the negative 19th power C. Call this 2.2b. The conductor as a whole is neutral, since there are equal numbers of protons and electrons. Using equation 2.2, we can see that the current of 1 ampere flows through a copper wire. The number of electrons flowing by a cross-section of the wire in 1 second is equal to 1 ampere, which can be written as 1c over 1s times electron over negative 1.602 times 10 raised to the negative 19th power C, which can be put into scientific notation. We could say that that's negative 6.24 times 10 raised to the 18th power electrons per second. Just for funsies, I was like, well, I wanted to see, right? Like, what does that actually look like? If I didn't want it, let's say I don't want it in scientific notation, and I just want to see what the actual figure looks like. Well, this is what the actual figure looks like. You can see that I moved the decimal place over to the right because in the exponential place, the power of 18 is positive, so we're going to move the decimal point to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And that is a very, very, very small number because there's a negative sign in front of it. But I mean that number is ginormously small, if you will. But now there's another issue because look at this number, it's a negative. How do we get a negative number of electrons flowing per second? How does that even, what's going on? Well, there are two possibilities. A, the electrons are flowing in the opposite direction as the defined current, or B, positive charges are moving inside the wire instead of electrons to account for that sign. Now, it's said according to my book, Practical Electronics for Inventors, third edition by Paul Schertz and Simon Monk, says that experimental evidence suggests that only electrons are free to move, not positive charges, as positive charges are fixed in the lattice network of the conductor. However, there are media in which positive charge flow is possible, such as positive ion flow in liquids, gases, and plasmas. But as it turns out, the first choice, namely electrons flowing in the opposite direction as the defined current flow, is the correct answer. It is A, the electrons are flowing in the opposite direction as the defined current, and that's why the number turns out to be negative. Long ago, guys, long ago, when Benjamin Franklin, and this is I put the time period that he was walking the earth, 1706 through 1790, when he was doing his pioneering work in early electronics, he had a convention of assigning positive charge signs to the mysterious tiny things that were moving about and doing work. At the time, it was unknown what they were. But then sometime later, a British physicist named Joseph Thomson, who walked the Earth in 1856 to 1940, he conducted an experiment that isolated the moving charges. But in order to do his calculations and properly record his experiments, the man had to use the only laws that he had available, that is, the laws that were formulated by the American scientist Benjamin Franklin. So the laws were formulated using Franklin's positive currents. However, these moving charges that Thomson had discovered were moving in the opposite direction of the conventional current I used in the equations, moving against the convention. So Thomson decided to call them electrons. So why do we care? Well, you might not care. It might not mean much to you, especially if you're not interested in detailed physics. But if you are, that's great. Either way, we could pretend ostensibly that there were positive charges moving around the wires and in electrical devices, and everything would work out fine because negative electrons going one way are equivalent to positive charges going in the opposite direction. So basically, the T is Thomson was like, no, no, no. Thomson was like, no, it's not positive. It's not positive charges that are moving in conductors. It's actually negative charges, and I shall call them electrons. But the thing is, negative electrons going one way is the same thing as positive charges going in the opposite direction. So that means that all the old formulas still work. And since we are working with all of the old formulas, it's feasible to adopt Franklin's conventional current, but just understand what's actually moving within the conductors, electrons. Here's a little picture that I stole. I stole it from a Practical Electronics for Inventors, the third edition. Or maybe I stole it from the fourth edition. The formulas. There should be an S there, but all of the formulas used in electronics, like Ohm's law, pretend that the current I is made up of positive charge carriers. There's no escaping this convention, and we are stuck with it. It's convenient to pretend that positive charges are moving, so when you see the term electron flow, make sure that you just recognize that the conventional flow I is moving in the opposite direction. So let's work through a couple of examples. This question, example 1, asks how many electrons pass a given point in 3 seconds if a conductor is carrying a 2 ampere current. And we're given this diagram, and the charge of the charge of one electron is 1.602 times 10 raised to the negative 19th power coulombs. And then it shows we have delta Q in this portion, this blue portion of the wire, and says that 6 coulombs of electrons, or 3.74 times 10 raised to the 19th power electrons. And we show this point. It says the amount of charge that passes a point in 2 seconds is denoted with delta t. Or showed that the electrons, these are electrons, that they flow to the left, whereas the conventional current flow goes to the right. Now, when I looked at this, well, my first issue was like, okay, the charge of one electron, like 1.602 times 10 raised to the negative 19th power. But then if you remember in our slide, it shows that the electron, it's given with a, well, there's a negative, it's negative 1.602 times 10 raised to the negative 19th power coulombs. But then in our diagram, there's no negative sign. And I'm like, what? Well, it turns out that you can think of the negative sign as a label for the type of particle that it is. But when you're doing the actual math to count how many charges are moving, you're using the magnitude. In other words, mathematically speaking, you're using the absolute value. So that's why that disappears. My next issue was I was like, okay, coulombs, right? I see that this is measured in C, like what's going on. Coulombs, it's the SI unit for electric charge. One coulomb represents the quantity of electric charge transported by a constant current of 1 ampere in 1 second. Where if you zoom in, like, and if you look at the ampere, it's simply the rate of flow of electricity, and it's defined as one coulomb of charge passing through a specific point in 1 second. So to interpret this mathematically speaking, you would say that 1 ampere equals um, one coulomb per second. But then it's like the C here is isolated. So what's going on? I'm going to try to isolate that C, and I'm going to do so by multiplying 1 ampere times a second and one coulomb per second times a second, so that these cancel, and now I have 1 ampere times second times the unit of seconds equals one coulomb. All I did was manipulate this algebraically, but it's still kind of confusing. If we were sort of just to like think this through more, we could say like the current is amps multiplied to the time, which is seconds. That equals the total charge, which is measured in coulombs, which hopefully that makes a little bit more sense. Because if you're like, if we look at this diagram and we're like, what is Q? What is Q? The Q, it's the total amount of like charge, the total amount of stuff, total amount of charge that's passing through this blue area in the wire. And it's saying that that total amount of charge is 6 coulombs. It's 6C. But then if you're like, okay, well, what's C? Well, C is just the label. It's the unit. It's the unit of measure. We use it to measure the stuff, the charge, um, and it stands for coulombs, as we know. So like if you have like a pile of apples, right? And you count them and you say, well, I have 6 apples. If you have a pile of electricity and you count the charge, you say I have 6 coulombs, or I have 6C. So Q is the what, it's the amount of charge, and then C is how we measure it, and the unit is coulombs. So coulombs, it's like if you like label something as like meters, coulombs is the unit of measurement, and Q is like what? It's how much, it's the amount. Anyway, that sort of helped me understand it, so I thought I would share. We're asked, what's the charge that's passing through the blue point in 3 seconds? So in 3 seconds, what's the charge that's passing through this blue area? Delta Q, the change in Q equals I, the current, times the change in time, delta T. In other words, the change in charge is equal to the current times the change in time. But what's the current? Current, the average current, I sub average, the average current equals change in Q over change. Okay, so the average current equals delta Q over delta T. That is the amount of charge that that flows past two specific moments in time divided by the time. Excuse me, divided by the change in time. That is delta Q, the amount of charge that flows between two specific moments in time divided by the change in time. Well, delta Q it's given as 6C, right? That's delta Q. Delta Q 6C divided by the change in time, which is given to us 3 seconds. Okay, so 6 divided by 3 is 2. That is 2 columns per second. Columns per second, by definition, is 1 ampere. 1 column per second is 1 ampere. So 2 columns per second is 2 amperes. So this is the same thing as 2 amperes. Now it's like delta Q equals the current times the change in time equals, well, the current average, which is 2 amperes times, so the current's average 2 amperes times the change in time delta T, which we know is 3 seconds, equals 6 amperes times seconds. The product of 1 ampere times second equals 1 column. So this is the same thing as 6 columns. 1 electron has a charge of 1.602 times 10 raised to the negative 19th power coulombs. So if we want to find the number of electrons, what's the number of electrons equal to? Well, we want to know like 6 columns worth of electrons. We're going to take this 6 columns right here, 6C, and divide it by the charge of electrons, 1.602 times 10 raised to the negative 16th columns. As I could write this as a fraction. 6C up top, 1.602 times 10 raised to the negative 16th columns. Like right away we can see that this here is gonna, these columns are gonna cancel out. Yeah, I can't do that in my head. 3.74535 times 10 raised to the negative 19th power. I'm just gonna rewrite this. 3.74531,835 times 10, which means that I'm gonna take this number, 3.74531,835, and I'm going to move this decimal place over 19 times to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there'll be a 0, 0, 0, 0, 0, 0, 0, 0.0000 with a decimal point here, which equals 374531835. And how many zeros is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then here, 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 here. Dude, that's a lot of electrons. That's crazy. That's so many electrons. So that's how many electrons would be in this region of the wire. It's a lot. Anyway, this could also just be approximated. This is the second example here. It says that charge is changing in a circuit with time according to Q of t equals 0.001 C sine of 1000 over S times t, and to calculate the instantaneous current flow. Current is just the flow of charge over time. If charge is moving through a wire, the current I is just how fast that charge is moving at any exact moment. And then in calculus, that rate of change is called the derivative. So we're going to set this up, and well, we're given an equation for the charge as a function of time, namely Q of t equals 0.001 times sine of 1000 t. So I'll just write this out. So we're given an equation for the charge as a function of time. Q of t equals 0.001 times sine of 1000 t, such that 0.001 is the amplitude or the maximum amount of charge that builds up. So like if we were to think about this graphically, then we have like a wave. So remember we're dealing with sine here, so we're gonna look at like our sine wave. This is not the best sine wave, but you know what? That's what we got. So so let's see here. Well, from here down and from here up, this is the amplitude. Now this is like the peak, also called the crest of the wave. And then down here, this is called the trough. Now this line would be the resting position, and honestly, the lowest point is the trough. And I want to move that because I want to just show you guys that this here, this is the wavelength. Well, sine of 1000 t tells us that the charge isn't just moving in one direction forever, it's oscillating back and forth like a wave. It is a wave, right? We need to use calculus to find the speed. And to find the current, we need to know how fast Q is changing. So we're going to use the derivative. I, the current, equals dq over dt. So this is the change of Q with respect to t. And now for this is like a chain rule situation because we can rewrite this maybe to make it a bit more clear. And now we can see that this is a composite function. And just note that I factored out that 0.001. And so, well, the chain rule can be written as follows. So that says that if y equals f of g of x, a composite function, then the change of y with respect to x equals f prime of g of x times g prime of x. And so we can apply this to what we have over here because it's a composite function. Well, excluding this 0.001, which we factored out. We're going to ignore that for now, and we're just going to look at this, and we're going to apply the chain rule. So the first thing that I would do when setting this up is I'm going to be like, okay, like what's the outside function? The outside function on the outside, it's going to be sine. So the outside function, we can call it f of u, where f is sine, and then u is just the stuff that's inside 1000 times t, but we're not going to worry about that right now. So f of u is sine of u, okay, but then we also need f prime of u, and let's see, f prime of u, the derivative of sine is cosine. So f prime of u is going to be cosine of u. So the inside function, we'll just call this g of t. Okay, and what's on the inside of this trigonometric function is 1000 times t. And so what that is 1000 times t. And we can also call this u because it's what's going to go inside of this sine function here, this cosine function here. So I'm going to bring this back over here. I'm going to say, well, what's g prime of t? What's g prime of t? Well, we want the derivative with respect to t of 1000 times t. And so, well, I'm just gonna right away factor out that 1000 because it's a constant. And now we're looking at just taking the derivative of t with respect to t. And it's like, well, the derivative of a variable, just a singular variable, it's just going to be 1. So what we're going to end up having is 1000 times 1, and that's just going to equal 1000. Okay, so when we look at the chain rule here, we need f prime of g of x. So f prime is going to be cosine of u, but we're going to put what g of x is on the inside of that. So g of x is 1000 times t. Or excuse me, g of t is 1000 times t, or g of x. We're using the terms synonymously. The variable is just a placeholder. So let's go ahead and we'll set that up. That's going to be cosine of 1000 t times what? Well, the derivative of g of x, which in the case is the derivative of g of t, so g prime of t. Um, so we're gonna multiply it by g prime of x, which is our g prime of t, and that's gonna be 1000. So we're gonna multiply this thing by 1000, and well, at the beginning, originally we factored out this 0.001, and we're going to have to multiply that back. So really what this is going to be is 0.001 times 1000 times cosine of 1000t. And so, well, one thing to note here is that like if you do like 0.001 times 1000, that's just going to be 1. So that means that the current I, that's going to be 1 times cosine of 1000 times t. And so that's our result. The final equation, 1 cosine of 1000 t, tells you exactly how much current is flowing at any second t. Um, the 1 is the peak current. At the most intense moment of flow, you have 1 ampere of current. The cosine shows the current is moving in a wave pattern, but it's shifted slightly compared to the charge wave, which was sine. So if you think about like sine and cosine, I'm gonna try to draw this as accurately as I can, but I'm no artist. That stuff is beyond me. Um, let's see. Try to draw some dotted lines or some guidelines here, just so I can try to get this as accurate as I can. All right, so if we think about our sine wave and its orientation, graphically speaking, in juxtaposition with the cosine, um, I tend to think of it as like sine, it passes right through the origin. So sine, it crosses through the origin, and then it peaks. Its first peak is at pi over 2, and then sort of just like falls back down. And then its lowest point, its minima, its trough, it's gonna be right at 3 pi over 2. And it's going to sort of just like, it's just going to go right back up. All right, and it's going to sort of like follow suit on the negative side, and that like it's going to have its trough, it's going to have its negative point at negative pi over 2, and then it's going to sort of climb back up, and it's going to peak. It's going to have peak right here. It's going to have its crest um, right at negative 3 pi over 2. So it's going to look something like this. I mean, granted, it's not perfect, but um, yeah, that's what we got. That's what we got. This is going to go back down. Okay, so this blue, this is sine of x. So cosine of x, it's complementary to sine of x. Cosine of x, it's gonna, well, it's gonna come in like around right here. And again, this is not perfect, guys, but it's gonna come around right here, and it's gonna cross over, right at this pi over 2. So that's where it crosses the resting point. That's where it crosses the x-axis. It's gonna have the same amplitude as sine of x, um, but it's just gonna cross over at different points. So I think it's gonna like cross over the x-axis like right about here, up, and it's gonna fall. But again, their amplitude, it's gonna be the same. Like this is not drawn to scale, guys, but I hope that you guys can get the idea. As for the negative side, well, it's gonna fall right about here. It's gonna have the same amplitude right here, and it's gonna cross over right at negative 3 pi over 2. And so like that. That looks pretty bad, dude. Honestly, I feel like I'm not doing this much justice. Desmos comes in handy when it comes to stuff like this because I just don't want to like spread like misinformation. This is like a drawing of what it's supposed to look like, kind of looks like that, but this is what it looks like graphically speaking. Um, a graph of sine of x and cosine of x. And so you can see that again, they have the same amplitude, same peaks, same crests, um, same wavelengths even, but they hit that x-intercept at different points. And so the cosine, it shows the current is moving in a wave pattern, but it's shifted slightly compared to the charge wave. Now, you could get a negative result, and when the math gives us a negative result, it doesn't mean that there's less than zero energy. It just means that the electrons have changed direction, and now they're flowing the other way through the circuit. So I could try to summarize this. The charge, which is denoted with a Q, is the total amount of electrons. The current, denoted with an I, is the speed at which those electrons are moving. And in essence, by taking the derivative of the charge equation, you can calculate that speed, which gives you the instantaneous current. So if we plug in a specific time within this equation, we get the instantaneous current for that time. Alright, so let's try to get some perspective on this. What's considered a lot of current and what's considered a little amount of current? It's a good idea to have an idea of comparison when you start messing about with electronic devices. So these are some examples that I have. A 100-watt light bulb draws about 1 ampere. A microwave draws about 8 to 13 amperes. A laptop computer, I don't know why there's an S there. But a laptop computer, pretend there's not an S there. A laptop computer draws about 2 to 3 amperes, and a toaster draws about 7 to 10 amperes. A fluorescent light, it's going to be 1 to 2 amperes. A radio or stereo, it's going to be 1 to 4 amperes. A typical LED, it's going to be 20 milliamperes. A mobile smartphone accessing the web, it's going to be 200 milliamperes. And an advanced low power microchip that is an individual one, it's going to be a few microamperes to perhaps several picoamperes. Man, there's a lot of typos in here. Hold on. An automobile starter is going to be around 200 amperes. A lightning strike, that's going to be 1000 amperes. And well, a sufficient amount of current to induce cardiac slash respiratory arrest, that's going to be around 100 milliamperes to 1 ampere. So yeah, that's how much it takes to die. These are my works cited. This isn't very important because I used all of these. These are the links, and I heavily relied on this wonderful, wonderful book that I'm reading. It's so good. It's called Practical Electronics for Inventors. You probably heard it. You probably heard of it, and you definitely heard me mention it. earlier in this video. So, um, Paul Schurz and Simon Monk, shout out you guys. So yeah, thank you for watching my video, and I hope you guys have a good day, good night, and good luck.